Applied Immunology from Brunel University, Oxbridge, Middlesex, England, and a PhD in Immunoparasitology from the London School of Hygiene and Tropical Medicine in England. For the past 4 decades, Emerita Professor Akwachi has taught and researched at the National Institutes of Health in Maryland and in Georgetown University in Washington, D.C. And then later on at the University of Ghana, Legon. Her teaching and research have focused on malaria immunity, immunoparasitology, immunopathology, immunodiagnosis, autoimmunity, molecular immunology, and vaccine development. She co-initiated and co-led the first National Institutes of Health International Center of Infectious Diseases Research, a research partnership between Georgetown University and University of Yaoundé 1 in Cameroon between 1990 and 2001. At the University of Ghana, she established the immunology unit at the Noguchi Memorial Institute for Medical Research in 1980 to 1983. She was the first female director of the University of Ghana School of Public Health and the foundation dean of the school, also making her the first female dean in the College of Health Sciences at the University of Ghana. She has served on numerous national and international committees and boards and received several awards. She is a former member of the Ghana Health Service Council and a former UNESCO chair for Women in Science and Technology in the West Africa region. Emerita Professor Akwachi won the 2014 Laureate African Union Kwame Nkrumah Award for Women in Science. She is the 2019 Laureate for the Clara Southmead Ludlow Award by the American Society of Tropical Medicine and Hygiene. She's a fellow of the Ghana Academy of Arts and Sciences and a fellow of the African Academy of Sciences. Ladies and gentlemen, let us welcome Emerita Professor Akwachi. Thank you.
Thank you very much, Honorary Secretary, for that warm introduction. Presidents of the Academy, Vice Presidents of the Academy, Fellows of the Academy, distinguished guests, our students, media, ladies and gentlemen, it really gives me a great deal of pleasure to introduce one of our brilliant lady engineers. I really am honored. And to talk on another rare topic of refining gold. Upgrade in gold recovery from refractory carbonaceous gold ores, the use of phanerochaete Chrysosporium. I had to find out how to say this properly. Yes. And so let me give you a bit of a profile, then she can give us the whole spiel today. Professor Grace Ofori-Sarpong is a professor of minerals engineering and currently the dean of the School of Postgraduate Studies at the University of Mines and Technology, UMAT, Kapwa, Ghana. Grace serves as a member of the governing boards of Minerals Income Investment Fund, Ghana Chamber of Mines Tertiary Education Fund, and the governing council of the University of Mines and Technology. In addition, she serves and has served on numerous national and international committees, including the Ministerial Committee of Inquiry on Health and Safety in the Mining Industry, the Publication Committee of the Ghana Academy of Arts and Sciences, the Committee of Independent Reviewers for International PhD Scholarship, and as Associate Editor of the Journal of Sustainable Metallurgy. Professor Ofori-Sarpong is actively involved in research and consultancy in the areas of precious minerals, beneficiation, aqueous processing, mine waste treatment, acid mine drainage, and microhydrometallurgy, among others. And she has about 80 peer-reviewed publications to her credit. Professor Ofori-Sarpong holds a PhD in Energy and Mineral Engineering from Pennsylvania State University, an MSc in Environmental Resources Management, and a BSc in Metallurgical Engineering, both from the Kwame Nkrumah University of Science and Technology, Kumasi. She is the proud recipient of the 2017 Elsevier Foundation Award for the Sub-Saharan Africa for her contribution in science and her positive role in inspiring and mentoring females to reduce the gender gap in STEM. She is the founder and president of Ladies in Mining and Allied Professions in Ghana, LIMAP Ghana, and a fellow of the Ghana Academy of Arts and Sciences. So audience, present, and virtual, I give you our speaker, Professor Grace Ofori-Sarpong. Thank you.
Thank you very much. Madam Chairperson, Emerita Professor Isabella Kwachi, past and present presidents of the Academy, fellows of the Ghana Academy of Arts and Sciences, my sponsors and family gathered here, partners and friends of the University of Mines and Technology and the mining community, distinguished invited guests, students, media, ladies and gentlemen. Good evening. It gladdens my heart so much to be a fellow of this great academy. And it is a pleasant opportunity for me today to present my inaugural lecture on the topic, Upgrade of Gold Recovery from Refractory Carbonaceous Gold Ores using the fungus phanerochaete Chrysosporium. I have an expectation today, and that is at the end of this presentation, I want my participants here to be acquainted with some of the key words that we use in the extraction of gold from its ores. So some of them are ores, mineral of interest, gangue, double refractory gold ores, biooxidation, sulfidic ores, cyanidation, carbonaceous matter, Preg-robbing, Biotransformation, phanerochaete Chrysosporium, gold recovery, among others. And I have this outline to help me sail smoothly through the presentation. So I'll start with some basic definitions used in mineral extraction. And these topics are mainly going to help us through how the fungus phanerochaete Chrysosporium can biotransform carbonaceous matter in gold ores with the aim of increasing gold recovery. And I will end with my humble contribution to science. So some basic definitions. It all starts with a mineral. When we talk about a mineral, it is defined as
a naturally occurring solid that has distinct chemical composition and structure. So examples of minerals, we have gold, we have manganese, iron, they are all minerals. When we have these minerals coming together as an aggregate, then we form what we call a rock. So in a rock, a particular mineral can be in substantial quantity. And so that mineral is used to name the rock, and it becomes a deposit. So we can have manganese deposit, gold deposit. Now, if this substantial mineral present in the rock can be extracted economically using available technology and selling it at the current metal price, then that deposit is upgraded to an ore. It passes as an ore. So what it means is that today, a deposit that we have today can change to become an ore tomorrow, and an ore today can change to be a deposit tomorrow. So when we talk about an ore, we can have two main parts. That is the mineral of interest and all other minerals, which together we refer to as gang, and that is the unwanted minerals. So we talk about gold ore, we have gold, and we have unwanted minerals or gang. Now in Ghana, we say that wherever you can dig deep enough, you are likely to find gold. So if we can dig under this building, we are likely to find gold. Because if we look at this, so this is a geological map of Ghana. So a geological map of Ghana, and all over we have what we call gold belts. We have the gold belts all over, and the gold belts host the gold. So wherever we dig deep, we are likely to find gold. But whether we will decide to extract the gold under this building will depend on whether it is the rock under this building is an ore or a deposit. So when we talk about gold ore, the concentration of gold in the ore is so small, such that it is expressed in parts per million or gram per ton. So if we say the grade of gold is, or the grade of gold ore is 10 grams per ton, we are talking about 10 parts of gold in a million parts of unwanted materials. In the gold community, if you talk about 10 grams per ton, it is high grade, very high grade. But if we try to express it in percentage, we are going to have 0.001%, and that looks like nothing. So this concentration of gold, it's spread all through the unwanted materials. And we are talking about 99.999% of unwanted materials. Aside that, the particle size of gold is also important. If the particle size of gold is, let's say, 0.5 millimeters and above, we refer to it as a nugget. It means it's big, and we can use gravity to remove it. But a greater percentage of the gold is actually smaller than this particle size. And we can be talking about less than 0.1 millimeters. So recovery of gold from its ores depends on the grade, the concentration, it depends on the particle size of the gold, and it depends on the kind of association that exists between the gold and the unwanted materials. So using these, we can broadly classify gold ores into two. That is free milling and refractory. Free milling is easier to treat, and we define it as that kind of ore from which about 95% of the gold can be recovered by gravity concentration and or simple cyanidation. It means we are dissolving into solution of cyanide. after we have crushed and ground the material to less than 1 millimeter. So we look at this simple flow chart. Looking at this, we have the gold ore. So we classify it into two: free milling, which is the easier to treat. It contains mainly oxides. So after grinding it fine, the gold in it is liberated, and we can move it through cyanidation, where we dissolve it and we get it out. On the left-hand side, we have the difficult to treat, which is called refractory gold ores. The refractory ores contain sulfides and carbonaceous matter as the most important refractory components to us. And even after grinding so fine, the gold is still locked up in the sulfides, and so it is not available for dissolution. For the carbonaceous matter, the main problem is that when we start dissolving the gold, the carbonaceous matter is able to pick the gold back into the solid state, and that will lead to losses. So, for any refractory ore, we have to pre-treat the components that are causing refractoriness. And we will talk about two main pre-treatment methods. One is roasting, which has been an old method. In roasting, what we are doing is that we heat the rock in the presence of oxygen so that we will cause oxidation of the refractory components. So if you look at these equations, we have pyrite here, sulfide, oxygen, and then we produce oxide and a gas. Arsenopyrite is also a sulfide. When we heat it, we will produce an oxide. This is hematite, iron oxide, which will contain the gold in the solid state. But it is porous, so the gold can be dissolved. And we are going to form gases. When we have carbonaceous matter, we heat it, we are going to produce carbon dioxide. So these gases are acidic. They can act as herbicides and chop off weeds. And they can also cause cancer. And so if we look at the diagram here, this is a picture that was taken in an area where roasting was taking place. And you can see that the vegetation is completely off. The second diagram here is in an environment where we are using biooxidation, and I'll talk about biooxidation soon. So biooxidation came to replace roasting because of the environmental issues of roasting. Now, we look at this diagram or picture here. We see these shiny things here. They are all sulfides. And in the middle, we have carbonaceous matter. So you see that in one particular ore, we have sulfides, we have carbonaceous matter. So we are dealing with two aspects of refractoriness. And such an ore is referred to as double refractory gold ores. This is a process flow sheet which incorporates biooxidation for pretreatment of refractory gold ores. So the reddish part is showing how we can incorporate the biooxidation pretreatment. If we are dealing with free milling, from comminution, we move straight to leaching or dissolution. So that's the difference. Now, the biooxidation is a microbial process. We make use of a mixed culture of bacteria. And the original ones that started the BIOS process are Acidithiobacillus thiooxidans, Acidithiobacillus ferrooxidans, and Leptospirillum ferrooxidans. These microorganisms, we call them lithoautotrophic iron and sulfur oxidizing bacteria. What it means in simple terms is that hemolithotrophs, they need inorganic chemicals that they will break down and get energy. They are living beings, so they need energy. And the inorganic compound they use is sulfide. So we have iron and sulfur in sulfide. So if you look at this equation, it's the same components we used in roasting. But in this case, we are using microorganisms to oxidize the pyrite and arsenopyrite. So these organisms will use iron 2 and elemental sulfur as their electron donors. They will use oxygen as electron acceptor. Because they are living organisms, they need carbon for their cell growth. Instead of using organic carbon directly, they don't do that. They want to make their own organic carbon from inorganic carbon. And the inorganic carbon they use is carbon dioxide. The diagram we see here is just showing how they are able to chop the sulfide from the rock. All right. So at the end of biooxidation, we have the Bioox concentrate, and that is the oxidized component of sulfide. But what happens? Because the bacteria do not use organic carbon, and the carbonaceous matter, so they will finish their work, but they will not touch the carbonaceous matter. So when we send the Bioox concentrate through leaching, where we dissolve the gold in cyanide solution, the carbonaceous materials are still part of the ore, and they will start taking the gold back into the solid. And that definitely will lead to losses. So this diagram here is showing us the serious effect of carbonaceous matter in gold ores. From the reference, you see 1984. So this problem has been with us, and researchers have tried to solve it ever since. What this diagram is showing is that we have gold in solution, and as we allow it time, the carbonaceous matter in the solid is picking the gold back into the solid. And so the gold concentration of gold that should be available for us to recover is not available because carbonaceous matter is taking it out. Now the problem is that even though we use carbon to recover gold in gold mining industries, activated carbon, those ones are, let me say, chips. So we can pick them and recover the gold. But the carbonaceous matter is fine. It's part of the ore that we are treating. So we are not able to get the gold out of it. And so when it picks the gold, it is lost forever. And this phenomenon is referred to as Preg-robbing. So how is carbon able to get gold onto itself? We will look at some 3 important facts about that. We have several theories that have been proposed, but the 3 most important we want to talk about today is that the graphitic structure of carbon is very important when it comes to gold adsorption. The oxygen groups on the carbon are also important, and the porosity of the carbon also very important, and I'll soon show you why. So we have these structures. They are all structures of carbonaceous materials, and you can see from here that some of the structures are very compact. You know, it looks very compact. Then we have a loose one here with oxygen functional groups. We have one with chains and some aromatic rings and all that. So depending on how the structure is, gold adsorption onto it will be affected. So people have studied how gold adsorbs, and some researchers have come up with this diagram here, which shows that the gold cyanide ion will lie on 3 of the rings. 3 of the rings. What does it mean? It means that when there's a break in the rings, it's going to affect gold adsorption. And then I also spoke about the porosity or the surface area. So if we look at the pores within the carbon, we have macropores, the bigger pores. mesopores, and the micropores. And research shows that the most important pore is the micropores. Now we can look at this diagram too, to also reiterate the fact that the carbon structure, the graphitic structure, is important for gold adsorption. So here we have different ranks of coal. We have lignite, bituminous, and anthracite. And maturity of coal increases in that direction. So anthracite is the most mature form of coal. And contacting these coals with gold solution, we realize that the anthracite is able to adsorb more, far higher than the other ranks of coal. So we tried finding the carbon to oxygen ratio, and it is very clear from this diagram that the left-hand side is carbon to oxygen ratio, and the right is gold adsorption. So the higher the carbon to oxygen ratio, the higher the gold adsorption. And that is highest when we have a more mature form of carbon. Now, looking at this, it means that anthracite can adsorb more. Why are we interested in anthracite? The anthracite grade of carbonaceous matter, if you look through literature, consists of about more than 50% of all the carbonaceous materials in gold ores. And here is the case, it can adsorb about 10 times more than the others. So there's an interest in finding ways of biotransforming anthracite. Some researches have been done, but the results show that most of these microorganisms are able to degrade more of the lower rank coals rather than anthracite. So the question is, can we try phanerochaete Chrysosporium, which is a fungus? And this fungus, it grows in the environment. So this picture is growth of phanerochaete in the environment, and this is growth in the lab. The fungus secretes oxidative enzymes. They are called lignin peroxidase and manganese peroxidase. They also produce hydrogen peroxide, which they use to activate the enzymes. And they are lignin degrading. Lignin is the most recalcitrant part of wood, but that is what they degrade. So it is possible that they can degrade other carbonaceous materials. And using that, I came up with the hypothesis here that pretreatment of carbonaceous matter using phanerochaete Chrysosporium can result in destruction of graphitic planes that are necessary for gold adsorption. That increase in surface oxygen groups on carbon will not help with gold adsorption. And that decrease in the surface area and porosity of the carbon will also not help with gold adsorption. And based on the hypothesis, my objective was to assess the ability of the fungus phanerochaete Chrysosporium to deactivate carbonaceous matter and decrease Preg-robbing, with the ultimate aim of increasing overall gold recovery. So, first, I used anthracite as a surrogate for carbonaceous matter in gold ores. So, that is ash received anthracite. And then I have my standard gold solution. So, anthracite is contacted with a standard gold solution to see how much it can adsorb. Then, anthracite is treated with phanerochaete Chrysosporium. So we get the treated anthracite, which was also contacted with standard gold solution. And the residual concentration of gold in solution was checked to find out how much has been adsorbed onto the carbon. And this equation was used to calculate in gram per ton, how much the anthracite has absorbed before and after the treatment. So I'll show you some results. This figure, the first one here, is showing percentage gold absorbed. And then we have the empty bars are the controls, and the shaded ones are the fungal treated carbon. So as received, control against fungal treated carbon. And from the diagram, we can see that the major changes that are observed are as a result of treatment with the fungus. Then the second diagram is also showing gold absorbed on anthracite in gram per ton. And we are looking at number of days used in treating the carbon. So we see that the as received absorbed as much. And as a result of the treatment, gold absorption on carbon reduced. All right. These are simply showing us that the fungus can be grown or can be used in several parameters, growth parameters. So for example, in this diagram, we are showing different growth media. So the first bar is showing us the as received anthracite, how much it can absorb. And the rest, these are all different growth media, and they are able to reduce the amount of gold that can be absorbed on the carbon. Then we have pulp density of the media, pH and temperature. So when we incubate the anthracite with the phanerochaete, Chrysosporium, under different conditions, the fungus is still able to act on the carbon. So the fungus has been able to reduce gold absorption. What is it that the fungus is doing to the carbon, the surface of the carbon, for gold absorption to reduce? So we use some characterization techniques. The picture here is SEM. So A is showing us the as received anthracite, which is showing a well-structured surface, and after fungal treatment, we see an amorphous surface. And such an amorphous surface will not help with gold absorption. And therefore, it's one of the reasons why the ability to absorb gold reduced. Then we have Raman spectroscopy. And this also gives us an idea of the structural components of the carbon. And looking at the peaks, all the peaks reduced. We are looking at the red one showing the as received, and the bluish color is the treated. So it's showing that after the treatment, all the peaks reduced. But of importance to us is the peak here, which is called the G band, and it shows the graphitic structure of the carbon. And from this diagram, that structure also reduced, and therefore it led to reduction in gold absorption. The diagram here also gives us an idea of the surface area and porosity. And from the treatment, the surface area of the carbon reduced, the porosity of the carbon, the pore volume also reduced. But the micropore structure reduced, the micropore volume reduced, whilst the bigger pores increased, and those ones are not good for gold absorption. Then this one shows oxygen on the surface of the carbon. And from this diagram, the message here is that if you look at this side, what we have here is carboxylic acid. So the green line is showing the biotreated anthracite, and the red line is the as received. So after the treatment, the oxygen bar or the oxygen band increased. And it means that we have more oxygen on the surface of the carbon, and that will not help with gold adsorption. So putting all together, we can come up with this mechanism, which is showing us that we have the native enzyme, which is secreted by the fungus. It's a heme protein. That's why we have the iron 3 there. So this native enzyme is activated with the hydrogen peroxide, which is also generated by the fungus. Once it is activated, it becomes this structure called compound 1. And you can see that it is positively charged. It's giving us iron 4, which definitely will not be a stable component. And it's a radical. That is why we have the dot there. So this radical will react with aromatic substance. That is the R. And carbonaceous matter is an aromatic substance. It reacts with it. It forms compound 2, an aromatic radical. Compound 2 can also react with another aromatic substance and form aromatic radical. Now this radical is what we are showing here, the dot and the plus. And it is not stable at all. So it will keep reacting in chains until it finally breaks up, and we have carboxylic acid showing here. So what we have spoken about is phanerochaete chrysosporium reacting on the surface of carbonaceous matter, reducing its ability to adsorb gold. But the objective has an ultimate aim, which is to increase overall gold extraction. So the last few slides I'm going to talk about are taking us through dissolution, where we are talking about gold recovery itself. So we have free milling gold ore, and that is the easier to treat ore. You put it in cyanide solution, you can recover 95% of the gold. That is a free milling. So we did that, and then we created carbonaceous gold ore by dosing 3% of anthracite into the free milling gold ore. And it also went through cyanidation. Then this carbonaceous gold ore was treated with phanerochaete chrysosporium, and it also went through gold leaching. So let's see the results. So the blue line is showing us the free milling gold ore, and obviously giving us a recovery of 95.5%. When the free milling ore was dosed with 3% anthracite, it became carbonaceous ore, and that is a high-grade carbonaceous ore. And when it went through cyanidation, the recovery was 54.8, about 40% decrease because of 3% carbonaceous material. Now, the carbonaceous material surrogate was treated with phanerochaete chrysosporium. And after cyanidation, this is showing us, the yellow line is showing us the carbonaceous gold ore that has been treated. And that gives us 82.5% recovery, as against 54.8% from the carbonaceous gold ore. So I want to summarize my presentation. In summary, we are saying that, or I am saying that, phanerochaete chrysosporium is capable of reducing the gold uptake ability of anthracite-grade carbonaceous matter. Reduction in gold uptake by the carbonaceous matter was expounded by using several techniques. And adsorption of gold on carbonaceous matter decreased as a result of the following: that the surface oxidation, which disrupt the continuous graphitic structure, thus decreasing the active sites necessary for adsorption. We have reduction in surface area, which will decrease accessibility of gold to the adsorption sites. And we have cleavage of bonds, leading to pore enlargement, and therefore the smaller pores that are most important for gold adsorption will reduce, and that will reduce the ability of the carbon to adsorb gold. Free milling gold ore with gold grade of 3.5 gram per ton was able to give a recovery of 95.5%. When surrogate carbonaceous gold ore was created by adding 3% anthracite to the free milling gold ore, the gold recovery was 54.8%. And when the surrogate carbonaceous ore was treated with phanerochaete Chrysosporium, the recovery came up to 82.5%. Ladies and gentlemen, my humble contribution to knowledge. My study demonstrates a potentially effective alternative pretreatment process that utilizes the fungus phanerochaete Chrysosporium in reducing Preg-robbing in gold extraction. The varied conditions used affirm that the fungus can degrade carbonaceous matter in several growth media and in a wide range of residence time, pulp density, temperature, and pH. My contribution to science is that I have expanded the frontiers in finding alternative pretreatment methods for refractory gold ores that utilize the fungus phanerochaete Chrysosporium. Professor Chair, please permit me to acknowledge some people here. First of all, I want to thank God for everything. And I want to appreciate my sponsors, most especially Mr. Ali Ibrahim, Dr. Charles Amwa. Thank you very much, Mr. Ali Ibrahim, Dr. Charles Amwa, Rabotech Group, New Excellence Basic School, University of Mines and Technology, Ladies in Mining and Allied Professions in Ghana. I want to appreciate my family and friends. I see the CEO of Chamber of Mines. Thank you, sir. Thank you. My Vice Chancellor is also here. Colleagues and partners from UMAT and Chamber of Mines and the mining community. Thank you so much. Thank you. I want to thank the Ghana Academy of Arts and Sciences, and I want to thank everyone here. Without you, this wouldn't have been successful. Thank you very much.
Well, thank you very much. Now, I don't think we should all run and digging the floors here to find gold. But clearly, our professor has shown us that a new potential of purifying gold, and her contribution, which she outlined really elegantly. Can we give her another round of applause, please? I told you we had a brilliant engineer here, and I'm sure a lot of us were listening keenly, especially the students. I hope you learned quite a few terminologies. I won't attempt to summarize, but a few take-home message that really what minerals are and what aggregates and rocks, and that Ghana is fortunate. We have gold deposits. The challenge is how to extract and the various terms, when it's a deposit, when it's an ore. I hope you all learned that. That's very important. And then the important thing is purification. Because if you attempt to purify things, you either destroy it and destroy yourself in the process, or you destroy your environment, which, I mean, you all know what cyanide does. And if cyanide is the only way you can get gold, then probably we have to forget it, because we'll be destroying ourselves and polluting our resources. But our dear professor has come up with an environmentally friendly process. And you see, not all microorganisms are bad. We do have those who live in ourselves and help us digest. And we have a fungus, which she's utilized. I mean, she went through a whole list of bacteria. So first, she went through the geological map of Ghana and the various particle size, which allows you to think that maybe it's possible to even extract. And then, if you want to recover gold, you have to think of the methods, the free milling and the refractory ores. I've learned, quite a lot for my humble immunologist here. And then we talked about the roasting, which produces a lot of sulfides, oxygen, and all that. And then Biooxidation, which brings out a lot of gases, which are also quite environmentally unfriendly. Then the microbial processes that have been tried, and then her contribution to science is that, and then the important thing is the carbonaceous material, which at the end product absorbs the gold. So you purify the gold and the carbonaceous matter absorbs the gold, so it's a loss. So her important method is bringing the fungus that takes off the carbonaceous material that allows gold purification. And so we end up with getting an 82% recovery by using this wonderful fungus. And again, let me pronounce it again, phanerochaete Chrysoporium. So we should all be running after this fungus. But clearly, she's made a contribution to the field and purification of gold, and to a credit. And often you don't see the in-between hard work, that the thought, the methodology, the processes, and this is where the scholarship comes in. So we thank the good professor for a wonderful exposition of her contribution to purification of gold. Thank you so much.
Thank you very much, Emerita Professor Kwachi, for those remarks. And that brings us to the end of this evening's event. But before we go, I'd like to acknowledge the schools gathered here with us tonight. And they are Ganata Senior High School. A round of applause for them, please. Accra Academy. And the Accra Technical Training College. Thank you very much for being here with us tonight. As we leave here, there is packed refreshment right outside this auditorium. Please pick up a pack and refresh yourself before you leave. And now, I'd like to ask you all to stand, please, while the speaker and the chairperson leave the podium. Thank you all very much.